Okay, this week we're going to take all the different pieces we've kind of learned and put them together to see how we can move air around. You think about it, density changes with temperature, density changes with moisture. We noticed that depending on how heating went, we might have different densities and maybe different pressures. And we've talked about air pressure and how the atmosphere wants to make everything the same. So all that contributes to moved air. And if you're going to make a forecast for tomorrow, you want to know where the air comes from, right? Because it probably isn't staying from what you have today. So let's look a little bit at how the air moves. So we're going to talk things like we have a low pressure here, just north of Minnesota right now, and a pretty good cold front moving down through here. Temperatures are in the mid 40s in the middle of the day back in here. So that's fairly chilly, at least to me. But notice the pressure gradient. Notice how the isobars stack up here fairly tight. We have 20 knots of wind at the surface here. Notice also it's blowing a little bit in towards the low pressure. Now, further east, we have less pressure gradient. We're getting some southerly wind out ahead of the low, along ahead of the front. And over along the east coast, we got a huge high pressure that's been sitting here all week, and it's just a little bit of an east wind coming in off the ocean. And really, not a really strong pressure gradient. If I was to show you a map back when Ophelia came through my house, you would have had this high pressure up here and Ophelia right here. And the pressure gradient was much, much stronger. And that's why I had 50, 55, even 60 mile an hour winds around the area. So that's the surface map. Let's just take a look aloft. We want to know what the winds are doing up there too. And here is the current winds aloft at 300 millibars. It's a good jet stream. Notice the jet stream here. Very strong winds coming into this trough of low pressure. So we had this nice low up here. We have this strong jet coming in and another jet exiting. We have actually 90 knots of wind there, 105 here, 125 knots here. So the jet streak is right in here. There's even stronger winds coming in. So with that, if I have that kind of winds momentum coming in, it's going to want to push this front on through much faster towards the east. So let's just take a look at this in the vertical. This morning, this is by Cincinnati, Ohio, we'll say. And there's a nice temperature inversion down here. What does that mean? Well, that means that the air got cold, right? Very dense. It's not mixing with the air above it. So whatever winds are going on down here are occurring just from some small pressure gradient, which isn't much, that was there. Notice the winds are southerly at the surface here. And right above this, as soon as they get above that in temperature inversion, they go to southwest and they start increasing in speed. And notice the peak winds are up here around 200 millibar at over 130 knots. Or not 180 knots, excuse me. So you can see that winds have picked up and changed direction as we go through the heights here. All of this plays a role in how the weather is going to change. Because if I was to look at another one of these further out west, I bet I would see something very different. Different bunch of winds here, different directions, even where the cold front's beginning to come through here. So let's look a little bit and try to understand a little bit of how this is working. So, wind and weather. That's what we're going to talk about. So what forces control the speed? All right, forces. What's a force? Did your car ever move down the road? Or did you ever have to push your car? Maybe I should put it that way. You applied a force to push that object, right? Push somebody out of the way. That was you applying a force. So your weight times the acceleration, how fast you were moving and picking up speed, is called a force. So a force is always changing in the atmosphere. And there are different forces that apply in the atmosphere. We have the air pressure gradient. You've been talking about that a lot. Centripetal force, which we're going to talk about as well. Coriolis, friction, and gravity. All of these work together to cause an air molecule to move across Ohio or across West Virginia. So the closer the isobars are together, the stronger the pressure gradient. The same would hold in the upper air charts that you see with contours. If you were to think about it, then that just would mean the 500 millibar slope was much steeper where the contours were very tight together. So if you looked at the horizontal, you would have a very strong pressure gradient. Another force, centripetal force. If you moved your car around the curve, you are generating centripetal force because you stayed on that curve. You didn't go straight. You managed to make it around the curve. What holds you there is that centripetal force, called center seeking, is always pulling back to keep you in going around in a circle. It's not independent, as it says here. Finally, we're going to talk about Coriolis effect. All right, the Earth moves. Unfortunately, it makes the physics of weather a lot more complicated because it moves. Think about it. If you were located 20 miles south of the North Pole, in one day's time, 24 hours, how far do you think you would travel in a circle if somebody was looking down at you from above? Probably not real far. You're only 20 miles from the very top of the world, so the top of the world doesn't move, right? What about down at the equator? Oh man, you're going 24,000 miles. So that is the force that's generated by the rotation of the Earth. In the northern hemisphere, it acts to the right. That force is stronger the further north you go. So when you get down to the equator, while you're moving, it doesn't have that force. While you're not moving and you're sitting up by the North Pole, you have much, much greater Coriolis effect. And interestingly, in the southern hemisphere, instead of forcing everything to the right, it'll force everything to the left. And here you can see how that works with the different pressure gradients around the world. Finally, we get down to right on the ground. Think about it. If you were moving an object up and down hills, that would be a lot harder than if the object was perfectly flat. Well, that's what friction's dealing with in the winds. So when you're moving an object across the land, especially the bumpier the land is, the more friction is generated and the slower the winds are going to be. Now, if I go over a lake or over a large body of water, I don't have a lot of wind from a lot of friction. So I may have a lot more wind. So that is why one of the things that happens for the sea breeze, for example, is over the ocean, there's no friction, hardly at all, holding the wind back. And as soon as it hits land, it's going to slow down because there's a lot more friction. That slowing down is going to cause convergence, which we've talked about, pulsing the winds together, which means there's going to be rising motion. Now, further up in the atmosphere, away from the boundary layer, away from the low level here, we get turbulence. And turbulence is when you've ever been flying in a plane or bouncing around up there. It's the air kind of moving back and forth in not a nice smooth flow. And the faster the wind is, the more turbulence it generates. So it's something that's very difficult mathematically to formulate, but it impacts how much motion of the air occurs. Friction is much stronger near the ground than it is further up. Gravity pulls everything down to the earth. And that is the key. It does not impact at all the horizontal winds. Everything's vertical. And Interestingly, because we have a rotating Earth, there's a second force for gravity on Earth called the centripetal force. It's very, very tiny in proportion to gravity, but it's there. So they're actually gravitation and centripetal force that helps to keep objects back towards the Earth. So all of these work together to move the air. So let's just start in the vertical. We know we have a very strong pressure gradient in the vertical, right? I talked about how you go 150 millibars in like a mile or maybe a mile and a half, literally, in the vertical. So that was one heck of a pressure gradient that's wanting to get eliminated by the atmosphere. However, gravity is pulling everything back down. So we wind up in equilibrium, called hydrostatic equilibrium. So the air parcel is balanced, same force as gravity pulling down, vertical pressure gradient trying to pull it up, and that parcel is just sitting there. Yes, we can move it, that parcel, begin to push it up. Maybe it goes up over a mountain. Maybe the air starts to lift from convergence or whatever, or down from divergence of loss at the ground, but it will move at a constant velocity, and that is the key for hydrostatic. Now, there are two other basic kind of winds. Meteorologists will like to try to simplify things as much as possible, and there's a geostrophic wind. We're taking two components of the geostrophic wind. All we're dealing with is pressure gradient and Coriolis effect. So we know that the Coriolis effect operates to the right of whatever motion is there. So if the pressure gradient is pushing an air parcel towards low pressure, as that air parcel is moving that way, it's going to be turned to the right. And eventually, it will reach a balance. And it literally will move in a straight line. That's a geostrophic wind. It's a balance between the pressure gradient and Coriolis. Now, we know that pressure, we saw the wind's motion of air goes around circles, like high pressure or low pressure. Well, with that, and those happen aloft as well, we're adding another force, not just the Coriolis force and not just the pressure gradient. We're going to add the centripetal force. It's a curved motion. All the centripetal force is doing is acting inward towards the center of the high or the low to keep the air moving around in the circle. Now, when we go down into the surface, we pick up friction. Friction is much greater near the surface. What that does is slows the wind down. Where the pressure gradient and Coriolis were balanced, they're no longer balanced because the motion has been slowed by the friction. If it's slowed, then the Coriolis effect is not as much. It's going to be a little less. So that is what allows the winds to move inward towards a low pressure and outwards away from high pressure. The impact of friction is that. Without friction, we wouldn't have that nice convergence in the low and divergence in the high. Interestingly, the atmosphere is a fluid. So if I have horizontal divergence at the ground level, then I'm going to have air that wants to sink down, take its place, and I'll probably have convergence aloft. Think about high pressure. Air is sinking in high pressures. So I want to look for areas of horizontal convergence aloft in order to know where I'm probably going to wind up with high pressures at the ground. And we talked about a little bit about the lakes and waters. So that is pretty much it. I hope you got a little bit out of this. Let me know if you have any questions on this.